Good evening and welcome to tonight's show from DJNTV, Disc Jockey News TV. Tonight's show is brought to you by Electra Voice, DJ Event Planner, DJ Trivia, Odyssey Innovative Designs and Cases, NLFX Professional, Promo Only, and the DJNTV Insiders.
DJ Event Planner will change the way you manage and run your business. Streamline all of your procedures and software into one easy-to-manage system. DJ Event Planner, the ultimate online planning tool.
Okay, wait for it, hang on. And now, ladies and gentlemen, the one and only Ben Stowe! Wait, stop! My trumpet section doesn't know when to stop.
And cut.
And that's our show for tonight. Thanks for playing along, everybody.
Well, it's, boy, with an introduction like that, it's great to be back.
Yeah, it's good to be back and doing a couple of shows here. For those of you wondering, this is Ben Stowe. Many of you have read about him, the man, the myth, the legend. Well, here he is tonight live, and he's going to be talking about a question a lot of you have, and we'll be getting into that in just a couple of seconds. And Ben, this is something that you and I we've intimated this a little bit, but what I'd like to do this summer, and we're going to talk about it live here on the show because we can, try to like get together about once a month if it'll work for you this summer, and we're going to because we've got questions that are coming in from people, and if it works out, gang, we're going to try to do this about once a month throughout the summer between, going fishing with our children and throwing the football at our children and playing softball with our children.
You have a much better family life than I do. My kids they're saints. Well, no, they're not. But I love my kids. I just I feel like I need to do more of those things that you talk about. But of course, I do want to be here for our viewers too. And I did apologize publicly at the Mobile Beat show. There were a number of people in the room that have watched the Tuesday night shows that you and I've done. And so I said, it's not John, it's me. I'm sorry. I said, I'm working to get back. He's been patient. So viewers, thanks for hanging in there. Just out there getting all that geeky experience you like to hear about. And, John, just today, I got a message from a viewer in South Africa. It's incredible the reach that
wow,
your little media empire has. It's always interesting to me when I get questions because I'm sure some of the things I say on the show viewers don't understand. But I get emails and Facebook messages from around the world because of this show. And if it were not for Google Translate, I wouldn't understand. So for those watching, really my only language is English.
And Google Translate sometimes is great and sometimes not so much because you can see it both ways with the broken English and such and how it comes together and verbs are out of place with this and that and the other thing. But a person can make do most of the time.
Yeah, I speak a little, very little, maybe not even conversational Spanish. I mean, enough to sort of get me around, I guess. I'm trying to learn more. I need to learn more. You
didn't watch enough Dora when the kids were little. I'm just going to say it right there.
But if you're in Lithuania, I have no idea what you're saying unless you send it in English. So
we'll try. We'll try the best. So tonight, let's jump into tonight's topic. We're going to talk about the kilowatts.
I got one too.
Yeah, look at this. Everyone's got a kilowatt. If you guys don't have a kilowatt, you're not in the Cool Kids Club. So you have to go get one right now.
I think probably a lot of people got them after the show we did maybe 3 or 4 years ago, which is probably a good show for remedial watching because it demonstrates the question that I think you're going to have me answer today, at least looking at the graphic I saw. And by the way, I just want to send out a quick thanks to Ryan from Spectrum Entertainment because I loaned my kilowatt to somebody. And I forgot who I loaned it to, and they apparently forgot also because I never got it back. Oh, no. And I mentioned that just one time, some while ago. Anyway, he sent me one. So I just wanted to send a shout out to Ryan for that thoughtful gesture. So
yeah, very nice, very nice.
And I'm not loaning it to anybody, so don't ask.
It's got my name on it. I licked it. Oh wait, now we're flashing back to my children do. So we'll get past that. So for those who aren't familiar with what a kilowatt is, can you give us a little layman's explanation? You notice, gang, I asked for a layman's explanation, not the Ben Stowe technical explanation, not the expert explanation, not the one that will make our head hurt. Layman's explanation.
Well, I'm so glad you said that because this I feel like is a really good time to throw this in. When I saw the graphic that said, "Can you get 1,000 watts from 100 watts?" Of course, we've been doing shows. We've done over 100 shows together. So I kind of know where you're going with this. Some time ago, viewers began a drinking game with our show.
You just couldn't even wait to get.
Every time I say it depends, apparently now you drink. Well, let me tell you, today, I don't know if I'll say that or not. There's a good chance that I will. But today, you're just going to probably want something to drink because there's math.
There's math. And
today is going to be a different drinking game just to numb the pain. So I'm just going to give you a heads up. So to answer your question, a kilowatt is basically a device that we can plug into the wall and plug another device into and monitor all kinds of fun and exciting things. We can monitor the voltage from the wall, but we can also monitor the wattage that the unit is using, the volt amperes that the unit is using, the amperage that it's consuming, which of course our circuit breakers are measured in amperage. And basically it tells us all kinds of fun things. This one will even measure the frequency of the electricity, which ironically today is going to talk about sine waves. And here we can see this little PF down here. That's power factor. And we just talked about volt amperes and watts, and that's the ratio. So anyway, basically lets you see all kinds of fun things. Here we can see how many, kilowatts per hour. I think the intended purpose of this was basically to help you save energy at home and find, vampire power, that sort of thing, and eliminate it.
Yep.
But it is a very cool, inexpensive way for us to see how much power something in our rig is using. And that, of course, we used in this show that I referenced a minute ago, where we had a 1,000-watt speaker or something. I forget exactly what it was. And we were rocking that thing, and we saw that we weren't drawing anywhere near 1,000 watts from the wall. So I got ahead of you. I apologize.
No, that's quite all right. That's quite all right, actually. Since I wasn't sure if you were going to have something to plug in.
I don't.
I do. Let's see. Will it show on the...
As you know, I just got off the road. I just
that...
finished driving about 10 hours. And there you go. Perfect. So there we can see you got your voltage in 120.8.
Yeah. Let's see. And I want to... And where's the wattage one? Is this one that will... There we go. So what I have over here is one of my little stage lights over there. That is maybe fluorescent, I think. So we're right now pulling what, 28 watts? Is that what I'm seeing? 28.4.
I gotta zoom in. Getting old is no fun.
I know, and I can't see it much better if I turn around. Yes, it must be the 28.4 watts. And if I wanted to go to amps, there we go.
See, and okay, that makes sense, right? So we know that our amperage should be our voltage and our wattage. So we would take our voltage times our amperage to equal our wattage. So we can see that math would work out there.
Mm-hmm, mm-hmm. So it's all proportionate.
So now the reason there's volt amperes and watts is that there are both resistive and reactive electrical loads. And so, that's a different show. I got to stop myself right there. Sorry.
I was going to say, that's going a little bit into a different direction.
If the power factor is 1, then volts times amps equals watts, but that isn't always the case. Volts times amps always equals volt amperes, but don't always equal watts, and that is a different show. So, no, that wasn't the part that's going to make your head hurt. That's still coming.
Oh, they're already talking about that they can't get enough alcohol. David's saying he's on medication. He can't get the alcohol. Be nice to him. Okay, great, we got it.
I can't advocate mixing medication and alcohol. Yeah. I'm not a pharmacist. I'm just a lowly geek here.
Just a guy who knows how to use a calculator and a slide rule. I'm going to plug that one.
Not too shabby with an abacus either. So.
Okay, so we've got the kilowatt. That'll give us an idea of the amps that a device is going to draw or the wattage that is going to draw. So we have that. And again, we did this in a past show, and we're going to be kind of revisiting a lot of the concepts to that. We're just not going to hook up a speaker tonight. The light was what you get. So we have that.
Go back and reference that show if you want to see it. But I think a lot of people already know that. They already experienced that. They say, how do I have a 1,000-watt speaker or a 2,000-watt speaker plugged into a circuit breaker and it's not tripping the breaker?
Precisely. And that's a tough one, because we've been seeing a lot of people talking about generators and wanting to get a generator to do this, that, and the other thing. And I took out a little 700-watt generator. It's a 900-watt peak, 700-watt inverter. And I was running 3 speakers with it and had my kilowatt on that. And I was pretty loud on those speakers, which I think are supposed to be, 1,000-watt speakers, whatever they were. But they
Well, remember, doubling the power only gains you 3 decibels, which, you know what? There's a little giveaway right there. Everybody just put that in the back of your head. We're going to see that again. So that's where having an efficient loudspeaker is very important. Now, so is having enough power. But it's all part and parcel. We're going to see how that all kind of comes together. I hope.
But that part would actually be more in the sound output, the SPL, not so much of the rating of the amplifier that is built into it. When it comes to our question of how can a Class D digital amplifier be rated at 2,000 watts and it's only pulling 50 watts from the wall, 75 watts from the wall. And
we're going to focus purely on the acoustical element of this, because there's another really slippery slope there where we start talking about dissipation and loss. Class AB versus Class H versus Class D, that sort of thing. So we're not even going to talk about power that's lost to dissipation. We're just going to focus on the acoustic element, because I think that's really the critical part. Mm-hmm. If anything, the dissipation actually will cause us to draw more power.
Give me a definition of dissipation.
Energy lost to heat. So think about the good old days when you and I were both young, and we were using Class AB amplifiers that weighed 1,000 pounds, and somehow we lifted them in and out of our trucks every day for gigs. But being in the cool Minnesota climate, we could also use those amps to warm our hands.
Fry bacon,
cook cookies, So those amplifiers were consuming power from the wall, some of which was going to make music, and much of which was going to make heat. And of course, modern digital amplifiers, modern, Class D amplifiers, which I shouldn't have called the digital amplifiers. That is really a misnomer, but that's okay, because that's not today's show. So just, you didn't hear that. But Class H, things with switching power rails, that sort of things, they're much more efficient. Another way to think about it is an incandescent light bulb, which produces some light and some heat, versus fluorescent or LED light sources, which produce more light than heat. They're more efficient at doing the job they were designed to do. And so that's what I mean by dissipation, is those amplifiers were less efficient in terms of producing musical energy as compared to heat energy.
Got it. Okay. So we have our power in, we have that, and then we have our wattage, what have you, coming out. What happens to this, what's this magical, mystical thing that happens that makes it so we see different numbers and different ratings and such, and makes us confused?
Well, there's 2 things, and we're going to dive really heavy into the math here in about 2 seconds. So get your drinks ready. Bottoms up, boys and girls. It's just water, by the way, I promise. But before we do, the other thing I want to talk about is if you look inside an amplifier, you're going to see a lot of capacitors, which are devices that store power momentarily. And so that allows that amplifier to essentially pull power at a gradual rate, store it, and then dissipate it into the circuit as needed for large peaks and that sort of thing. So that is one way that the amplifier helps kind of smooth out that consumption. But another way is just thinking about what we're actually doing, what we're actually making in terms of music. And I'm going to go to a graphic here, and gosh, I sure hope this works.
Yep, sure.
But you know what? If it doesn't, it's a free show. So stop.
Exactly. Yep. You guys get what you pay for.
All right. Let's see here. It has been so long since we did a show. I forgot how to do this. Let's try this.
Share in the bottom there. Here we go. Perfect.
Okay, got it. Share. All right. And you see
we're seeing the peak amplitude, and then you and I are still up. This is the kind of cool thing since we did our last show with this is we both are on there. I don't have to do any fancy graphics anymore. We're right on the side. It's pretty cool.
Oh, well, all right.
So yes, there's no picking our nose whilst we're showing screens anymore. Not that ever happened too much.
No, not me.
Anyway,
I don't know how people you get on this show, but
yeah, well, there is a reason why they. Okay. Cool hand. We'll get to that question later. So if you guys have questions, put them in the chat room. We'll get to those later. So I'm sorry, Ben. I wanted to make that so people knew that we're not ignoring them because there's going to be a few good things that we need to talk about.
I'm sure there will. So, all right. If we take a look at this chart here, this picture, you can see I've got a sine wave in blue, basically a pure sine wave. And we can see the peak amplitude demonstrated there, okay?
Mm-hmm.
And the word of the day that we're going to be talking about is crest factor. That's really, I think, the biggest single underlying reason why we have these two numbers, 1,000 and whatever for amplifiers. Some people feel like, well, maybe the audio manufacturer is lying to me. And that is a possibility. I think there are some that sort of stretch things to the breaking point of the truth. And there are others that I think just completely make things up. But the fact is that I think they just honestly, they just make things up. But there are particularly your big brands, they're really committed to at least trying to not murder the truth. And you can see where even if they're completely 100% honest, like many of them are, it's still going to cause this large variation in numbers. So that I just wanted to kind of put that out there. Taking a look at the next picture here, now we can see the RMS amplitude here, and that is the root mean square, which is basically the effective power of that sine wave. Okay, and our crest factor is the difference between the peak and the RMS measured in decibels. So because this sine wave is on and off, basically as it's cycling, it's not always on, like DC circuit. So it has this RMS value, the effective amount of power. And if we look at this here, and remember when I said when you double the power, you gain 3 dB, or you have the power, you lose 3 dB?
Mm-hmm.
Well, this sine wave, this perfect sine wave, is basically on half the time and off half the time. And by no small coincidence, and you can work the math yourself if you'd like, but our crest factor here is 3 dB. So there we can see that we have this crest factor of 3 dB for the RMS value of this sine wave. This would be about the most challenging thing for your amplifier to produce. It would struggle to do this long term because of this very low crest factor. Now, of course, it would struggle even more if we had a DC circuit, which would be 0, and that just wouldn't work, right? So this would be very demanding on an amplifier. Music can have crest factors ranging from 6 to 9, 12, up to 20 dB. So there can be a huge crest factor in the music. And that makes sense because and speech is even worse, because as I talk, there are peaks in my voice, and then there are moments of almost silence, and mm-hmm. So we have to think about the effective power over time and how much power that amplifier is actually producing. It can only produce a certain amount of power peak anyway. Once peak is peak, but it's not always producing peak power. Okay, everybody with me so far?
Okay.
let me see if I can figure out how to not share this one.
Yep.
And I'm going to share something else. We're going to do this. All right. What we have here, you can see hopefully is a shot from Audacity.
Yep.
Which is a free audio program. Anybody can get it. I picked that one because a sine wave. Is that obnoxious or what? I don't know. Could you hear that?
Yeah. Yep. I mean,
can we do it again? No, I won't do it again. All right. Let's zoom in on this real quick. And when we start zooming in, we can start seeing some definition appear here. And as I zoom in, now we can see this is our sine wave. Okay. There's our sine wave. Okay. Now what I'm going to do is I'm going to analyze a section of this, and it's going to show me, can you see the contrast analysis screen? All right, let's try this.
There we go. Yep, I can see it.
Okay, so here is the contrast analysis of this track, which is a sine wave, and as expected, it's 3 dB. Okay. So just in case you need proof, there's the proof. Let's see.
Yeah,
there has got to be a way to share more than one window.
Yeah, you can share the whole screen, but then it, like the
it's going to really confuse people.
All right. It'll really be
so
messy.
let's go to.
There we go.
Let's go to this now as a music file, and the only wave file I had on this machine is I hastily prepared for this show. So now we can see, that there's a difference from the blue bar that we had earlier, right? Before it was just a consistently blue bar, and now we can see at least there's some changes here. But let's zoom in on this real quick, just for fun. And we can see that this is, in fact, definitely different content, right? So I'm going to make the copyright police mad here if I play this, but you can see how that is changing and pulsing, and it's not a consistent thing like the sine wave was. Okay.
Sure.
So let's do this. Let's stop share on that. All right. Selection. I'm so sorry that you can't see this. Just bear with me. Hopefully you can see it now. Okay. So what I'm going to do now is I'm going to measure this song, and there we can see that we have a crest factor of 12.5. Okay. So substantially bigger crest factor than we had with the sine wave, right?
Okay. And that sine wave that we were looking at initially, that's the power coming in. Am I following this correctly?
That's the music. That's the signal.
Okay.
So that tone that we heard earlier, and that just happened to be 500 hertz, and it could be anything. They're all going to look the same, basically, when they're zoomed in like that. Of course, the higher the frequency, the faster that cycle is going to occur per second, but it's still going to look like our drawing of a sine wave. And so that is the tone. Now, without getting into the real, crazy specifics here of Fourier and complex, fast sine waves and that sort of thing, that song we just heard is also composed of sine waves, just lots and lots and lots of them. And at varying intensities and varying frequencies, as is my voice and all those sorts of things. And obviously,
so then the sine wave we looked at, the individual 500 hertz sine wave, is just not all at the same dynamic range, i.e. volume, that our song is.
Right, because it's consistent. It has a crest factor of 3. It's going to consistently be at that level. And if we ran a sine wave at peak output through our amplifier, that would be very taxing on that amplifier and loudspeaker. Even though very difficult for that.
Even though it doesn't have the decibel range that we're seeing on the song.
Correct.
Just because. Okay, that's interesting. I would not have guessed.
Well, it gets into, I think we did a show on why speakers fail. We talked about energy over time.
I have to play dumb for this show, Ben.
Oh, I'm sorry. Well, so viewers, here's a challenge for you. Go dig back through YouTube. And John, here's a challenge for you. Come up with better tags on us fail. And that's where we're talking about energy.
And we showed
sorry, John, I missed you.
Yeah, we showed some fried voice.
5. Okay, we've got here. We're just going to use this song as an example. So we have our crest factor of 12.5, a really easy number to work with. So we're going to go with 1,000. Okay, our V minus 12.5, which is our crest factor, right? 12.5. We're going to end up with 17.5. Okay, divide that by 10, we get 1.75. And I'm going to, you know what? I'm going to do this. Hang on. I'm going to share this with you. So, okay, can you see this calculator soup screen?
Yep.
All right. This is pretty handy that I can just pop this right up for you. So I'm going to take, now, again, if you didn't follow along, I'll just repeat it, but it isn't necessarily that you have to know this, but it's fun to know things, right? So we took our 30, which was 10 times the log of 1,000, minus 12.5, and that gives us 17.5. And then we're going to divide that by 10 to get 1.75. And then we're going to take 10 to the 1.75 power. It's hard to say. And we're going to calculate that at a crest factor of 12.5. Our average effective energy is 56 watts. Hard to believe, honestly, right? People are going, no, it can't be right. So let's do something else we know. Okay, let's clear this. So our sine wave has a crest factor of 3, which we know. So let's take 30 minus, stop it. There we go. And 2.7 for our exponent. And here you can see that now we have 500 watts, which is exactly what we would expect at half the power of 1,000. So the math bears itself out. So let's do this again, just for those who want to have their heads exploded. That 1,000 watt amp, RMS, producing 1,000 watts. It's producing 1,000 watts sometimes. It's producing far less other times.
So let me just put.
Who's drinking?
Let me just put. So if I would take that 500 hertz tone, and if I would take that and put that to my favorite powered speaker, and push that to a point, I would be taking more energy to create that, and I would see it in my kilowatt.
Absolutely. Absolutely. Your amplifier is going to be working much harder, and those capacitors are going to drain faster because it doesn't have these momentary transients. It has a consistent output of a crest. I wouldn't recommend doing it, I guess, is the short version. Unless you have a sacrificial speaker. I know sometimes manufacturers send you things to test. Then by all means. But viewers, don't run a sine wave into your speaker for an extended period of time just to see what will happen, because I can tell you what will happen. So you're stressing the system. If you're running it at peak, so if you're truly hitting those peaks at 1,000 watts, you're drawing an RMS of 500, which is interesting. We think about, if you look at the measurements, typically our dB factors from, we've got, program, continuous, and peak, 3, 6, whatever dB. So makes sense, right?
That is, I guess I didn't realize that the variation in music had such a major, was that
well, and
large
think
of a
about
player?
it, if our crest factor was 20, it would be even more dramatic, be way more dramatic.
So in a case of a crest factor of 20, what would we see on the other side for our
Okay. Let's go back to our calculator. Okay. So if we have a crest factor of 20, so 30 minus 20 equals 10. Okay. 10 divided by 10 is 1. And so then we're going to take 10 to the first power, which of course is still just going to be 10.
Yeah.
Right. So now we're talking about basically 10 watts.
10 watts of power would be able to
on a 1,000 watt amplifier. Now, here's another, we can take this another direction. So let's go back to the sine wave thing, and let's talk about the loudness wars, and let's talk about the heavily compressed music that we have today. We have much lower crest factor. You know what? Bear with me. I can do this. So just bear with me a quick second here.
Wait, I can put on some while we're.
Oh no.
No, huh? No. Oh, okay. Sorry. Just thought it would be, kind of setting the stage and kind of getting us ready.
It was good. No, I think you should keep with it.
Yeah.
So we're going to make a very heavily compressed version of our song that we had earlier. All right. Okay, so here's the same song.
Yeah.
And it sounds much louder because we just compressed the daylights out of it. The peaks are the same. We haven't exceeded the peaks, but we just compressed the daylights out of it. And what we can see, we've got more average energy over time. So let's do the same thing we did before. Let's go analyze, contrast. And you can't see that, so let me share that. Hang on. Now we have a crest factor of 9.4. So we've reduced our crest factor from 12.5 to 9.4 by increasing the average amount of energy to this song. And this is what's happening with a lot of music today. It's called the loudness wars, where they're increasing the average energy by compressing it. And so we are, in fact, heating up those loudspeakers and stressing the components in our system much more today. Again, heavily compressed music could have crest factors under 9. So, if we take a look at this, get out the pen again here, 30 minus 9.4, 20.6. 0.06. So let's go back to our calculator. Now we've effectively doubled the energy.
Yeah, we were at 56 or so before.
Which, now I didn't just tell you this up front because I kind of wanted to take the long way here, because I'm hoping that some people are kind of watching this and going, oh, that's starting to click. The difference between 9.4 and 12.5 is essentially 3, which is double the power, right?
Mm-hmm.
It's
I see what you
always,
did there.
Yeah, right. And I would love to say that I planned that with the compression that I chose. That was just lucky. But anyway, we can see the result here, that we are effectively running twice as much power now by compressing that song.
So now let's take those two songs, in essence, the before and after compression. If we would play them, if we would set the gain structure on the board identical for both tracks, which one would sound louder? One is using 56 watts to create the noise or the sound, and the other one's using 114. Which one would sound louder, or could we be able to hear a difference with the two?
Well, let's see. I can't show you two of these together, it appears. But let me just play them both, and I'll let you guess. And again, I don't know how this is going to sound on your end. So here is track 1. Okay, here's track 2.
Okay, so track 2 definitely sounded like it was louder in that little thing.
Okay, so I'm glad that came through okay. Which one do you think was track 2?
In that situation, I would assume, because when we saw the graphic representation, and when you compressed, it seemed that it made it bigger, that area of the song larger. So I would guess that track 2 was the compressed one.
You're right. Track 2 is compression. So here's track 1. Track 2.
Oh, wow. So there's a definitely noticeable difference between the two.
You hear this all the time, by the way, when you watch TV, heavily compressed commercials. Sort of jump out.
That's where that comes from.
So, we sort of strayed a little bit from how do we get 1,000 watts out of 100, but I think that we covered all the fundamental things that are behind that, and it makes a lot of sense where, again, some people are probably feeling a bit ripped off that their 1,000 watt amp is only, consuming 56 watts, but it isn't the amplifier manufacturer that's misleading you. Nobody's misleading you. That's just physics.
Mm-hmm.
And again, that depends on the program material. So if anybody's guilty, I guess it's you. That doesn't mean, though, that playing something with a lower crest factor is better. That doesn't mean that's the right solution. It just helps us to understand how 1,000 watts peak translates into real energy.
And
it gives us a chance to play with exponents. So, and it's always a good time.
That's always fun. I mean, whenever there's a party, the first thing we want to do is pull out the exponents. Hey, let me show you how I do my exponents. No.
Yes. No, be there or be squared.
I see what you did there. Yeah, I got that. Brolance was asking, how does and I'm going to change a little bit. How does dynamic range fit into what we're discussing here?
Well, that's kind of what we're talking about, basically. The difference between the peak parts of the song and the lowest parts of the song and the average parts of the song. So, the really important thing here is the average energy, that crest factor. But we're basically talking about that. So, and it all comes into gain structure, and that's another show. And so,
another question. The compression that you're referring to that we did to that track, is that similar to the compression that we hear commonly used for MP3s, that it's compressed down to become this smaller file? Or is that a different beast?
That's file compression. So basically what we're doing there is they're using algorithms to take out parts of the material that they think you won't notice. They're using algorithms to take out parts that are alike, and so then it can be replicated, put back together, basically uncompressed. But that's really entirely different. What we're talking about here is taking a signal that would otherwise exceed the peak output of the system, i.e., the voltage, from our signal to, and we have our signal to noise ratio there. We don't want to exceed the peak voltage, but we want to be above the noise. Sorry, I kind of strayed in the middle of the sentence there. But what we're doing here is, instead of allowing those peaks to exceed, we're compressing them back in. So that could be a vocal transient. That could be something else. We use compressors all the time in live sound, to make things actually sound louder. We just saw that. Mm-hmm. But also to help things kind of punch through and to shape things and define things. So no, we're talking about basically peak compression right now, not file compression.
Gotcha. In other words, the bass that we have in our songs, of course, the waves of those, we've talked about that on other shows where they can be very long and drawn out. And bass stresses speakers, as we've talked about in the past also. Is that because the makeup of a low frequency bass signal is closer to that sine wave that we were talking about?
Well, probably has more to do with the fact that the more energy in it. There's a lot of energy in those low frequency wavelengths. We're moving the cone further. It's just a lot more going on there. If we tried to take and somewhere I have one here, you've seen my pile of junk in here, but if we're taking that small tweeter, which is designed, a diaphragm or something that's designed to move, millimeters, and we're trying to make it move inches like a low frequency driver would, obviously that's going to be a really big problem. So, I guess long and short of it, it's not necessarily that they're more like sine waves, because all of the frequencies are sine waves. It's just that the sine waves are bigger. They're longer.
Okay.
By the way, sidebar to that, people sometimes say that they refer to them as slow-moving bass waves, and that's not true. The speed of sound is identical at all frequencies, so they're not slower moving. They just consume a lot of energy
to get there. Let's see, continuing up through questions here. So if you guys have got questions, please put those in the chat here on YouTube. I didn't even check and see Facebook.
Keep asking. I'll keep Googling as fast as I can.
Yeah, exactly. I'm giving you a little more time to Google out. somebody was referring to the ETX specifically, where the subwoofer has a rating of 1,800 watts and the top had a rating of 2,000 watt amps into these devices. Does that lead to an unbalanced sound system? Is basically the question.
No, first thing I want to say there is obviously it wouldn't be an unbalanced sound system because they designed these things to work together. So it'd be silly to design something to work together that doesn't. And I know a lot of the engineers at Electro Voice personally, and I know what these guys do. They're not just making this stuff up. They're not just phoning it in. I mean, I think sometimes people think they are, but when you see the engineering process firsthand, as I know you have, John, you realize these guys they could probably be working at, NASA's JPL too, just as well. So they're very smart and they're doing really, really great things. In fact, before I answer the question of why the wattage is different, it's really amazing when we think about how much more compression is in today's music and the loudness wars. It's really amazing that we don't have stuff blowing up on a daily basis. Equipment 25 years ago was just simply not made to withstand these same rigors. They made some good stuff back then. I'm not saying they didn't, but I'm just saying the stuff we get now is so much better. It sounds so much better. It's so much tougher, bang for the buck that we pay for it. Because these guys just, have these awesome engineering resources, and that's not exclusive to Electro Voice. That's I'm talking about a lot of great loudspeaker manufacturers here. The biggest difference there, though, is in a top like an ETX top, you have two drivers. You have a high frequency and a low frequency, and so there are two amplifier channels, and they're going to add them together when they give you that number. Now you can bet the tweeter is probably only getting 200 watts. I mean, it doesn't need very much power. So that 15, or 12 or whatever might be getting the other 1,800. And then that subwoofer, same thing. There's only a single driver there, so you get 1,800 watts.
And again, they're all designed to work together and be balanced.
Yeah. One thing that we should really talk about that I kind of mentioned it a couple times, but I guess I never really drove it home, not to my own satisfaction anyway, is that remember, you only gain 3 dB when you double the power. So watts is meaningful when it comes to loudness, but not really. Certainly not to the degree that you should go shop for a X watt speaker. Mm-hmm. That doesn't mean much. And I think we did cover that in the show that kind of led to this show. This is the sequel 4 years later, I guess. But
we're pretty quick. I mean, let's face it.
How many years? I look like younger? Go watch that show. Yeah.
Let's see. CF Karaoke's asking if this concept is similar to the microphone preamps.
Well, sure. A preamp is just an amplifier. We're talking about the same thing. A microphone preamp is taking, a couple millivolt coming from a moving coil of a microphone or, whatever. Obviously, the output of an electric condenser or something has its own amplification built in, but, and we're bringing that up to a mixable level. So all the same principles apply. Inverse square law, losing 6 dB as I move the microphone away from me, doubling the power, gaining 3 dB. All those sorts of things are a part of this. Now, we're talking about such small amounts of power here for microphone preamps. We don't really have to worry about, so much about the, I guess, cooking a preamp on a board. We're not working them that hard. But things like crest factor are important, though. We're only going to get so much peak voltage out of that circuit, and so. Yeah, it's all related. It's really fascinating. And if you start looking at things like crest factor, you'll see that it applies to all kinds of things, not just audio waves, radio waves and all kinds of things. It's really been fascinating to me over the last quarter century of my career to see how these things just get repeated all over the place. You start doing RF training and you think, oh, I learned that in audio training. It's kind of related.
I've heard that song before. Where did it come from?
Yeah, pretty much. It really does start to make sense after a while. So it really does.
So let's stick back. Let's jump back to the microphone because the question then the second part of it was placing a compressor on your mic. And as I look at my board here, that is this microphone that I'm using right now. I have a compressor knob on this, and it just is basically from low to high as I turn. What is that compressor knob doing to my microphone?
Well, In the simplest of terms, and in the live sound world, we have some really awesome, fun compressors, and there are different types and styles of compressors that people would use, musically speaking. I use a compressor on a kick drum all the time to actually help it be more defined and more punchy. But on a vocal mic, I probably, would use that compression to avoid transients. Especially something like you've got where it's basically just a low to high. You're not really shaping the contour of that compression much. You're not, tying it to other channels for, listens and that sort of thing. You're just saying, okay, when you exceed this peak, compress it back in so that it doesn't exceed that peak and, overdrive my system, as it were, And so what we do then is we still have an increase in the average amount of energy, but you no longer have that transient that would be outside the bounds of what your system could produce. One way that we could visualize this would be that if such a transient occurred and it caused a loudspeaker cone to overexert, it would basically jump out of the speaker.
Sure. Yep.
So that's one thing we could avoid. Maybe, dropping a microphone, God forbid, that compressor might prevent that from, that transient from getting through to the system.
So then as a person, in a case of a simple one, because there are compressors on many boards have a very simple compressor.
Yeah.
Is it something then that would be that they could turn it up too high and cause damage, or is it something if they were too low they could cause damage?
Lose the dynamic range of your vocal. You can lose the really the definition and the clarity because we start pushing things together. Most compressors also have makeup gain. So we start pushing up the bottom and pushing down the top. We're kind of pushing everything into the middle. So we can use that to sort of contain a vocalist that's all over the place. Maybe they're too quiet sometimes and they're too loud other times. We can sort of push them into the middle, but we're squeezing those peaks closer together too. So we're taking that dynamic range, which is the other question that we had a little while ago. We're taking that out. Compressors are kind of the opposite of dynamic range,
And again, somebody wanted to give a differentiate that concept from a limiter.
Well, basically, compressors have ratios. Again, on your board, you just kind of have a knob of some kind. But compressors have ratios where I can say once this threshold is met, I'm going to try to draw this with my hands. Mm-hmm. And here's my threshold. So once the threshold is met, I want you to start to compress that signal at a ratio, So maybe like a 2-to-1 ratio, 4-to-1 ratio. Basically, an infinite ratio is a limiter. Let me see if I can do better on a piece of paper.
Yeah, I think you gave a pretty good good example. Yeah, I think so. I think that was and a limiter doesn't do anything on the bottom. Where you were saying that a compressor, you can bring them up a little bit and keep them in that middle area. A limiter does nothing on the bottom. It's just the top is all the limiter does.
Yeah, unless you use a compressor with an infinite ratio or even like a 10-to-1 or something that's really high. And I feel like I have a picture here I can show you.
We've had pictures in the past of this.
Yeah, maybe I don't. I know I do in PowerPoint slides and things, but I apologize. I guess I just can't track it down real quick on this computer.
Yeah.
I think but anyway, that's a fundamental difference. And there are different types of limiters too, and that we could do an entire show on limiters. We won't. I think it's probably beyond what most of our viewers maybe want to see, but. Because we can start getting into, those different types, peak limiters and that sort of thing, which does confuse people a little bit on some of the modern loudspeakers. They're saying, why am I seeing this light as opposed to that light? And this light means it's a gain structure problem in your system. This light means you're exceeding the system, So we spend some time walking people through what those differences are, and understanding why you're getting this limiter versus that limiter, or clipping is different than limiting, for example.
Mm-hmm. So many variables, so many words. Let's
keep kind of guys like me employed.
One last area. Of course, the wattage of the speaker. You mentioned that a few minutes ago that the wattage doesn't always have a meaning to the eventual ability of the speakers to make sound at a high level. What is the greatest factor in determining the SPL of a speaker? Is it the quality of the cones? Is it the quality of the amplifier? What would lead to a speaker being more efficient compared to less efficient?
I don't mean to be glib, but I think that's like asking, what chain makes a chain the strongest, or what, I mean, of course, the answer is, it's only as strong as its weakest link. So it is really the sum of all parts. Good cone design is going to be important. Good cabinet design is going to be important. A speaker without a cabinet isn't very effective. Processing, the amplifier, all of those things are going to play into it. But what it really comes down to is when we put all these things together, and they've been engineered and refined and refined and refined. You and I've had the good fortune of being in places like the Electro Voice headquarters and seeing plain wood boxes that are early prototypes that will just continue to get refined and tested and refined and tested and changed, and sometimes just thrown in the garbage. They'll abandon a concept. And of course, modern computer modeling has helped a little bit with speeding up the process. But what it really comes down to is when we take this finished product and we put 1 watt of power into it, what do we get out? Because doubling that to 2 watts will gain us 3 dB. Doubling that again to 4 will give us another 3. And we know this. Mm-hmm. So it's really important. What do we get for that first 3? Now, there are engineering is always a series of compromises. There are things that we have to think about. Do we need it loud? Do we need it musical? And we kind of want both, but
in our world. Yeah.
I mean, do we want brute force or do we want really accurate and musical? Some of the most musical sounding amplifiers are horribly inefficient. So compromises have to be made along the way to achieve that mutual result. Same thing with loudspeakers. And obviously, again, like I said, we're living in this fantastic golden age where they have lasers that map the surface of the cone in movement and help the engineers to understand how they can design these loudspeakers better. But the fact is that something always has to give. We're making them louder, we're making them more musical, and we're making them take more abuse because we're giving them more abuse with the more compressed signals that we have. So as far as your question about wattage, it really comes down to what do we get for that first watt?
Good. I think we'll wrap it up right there. We've got a lot of stuff with tonight's show. For some of you,
all our viewers are completely drunk now, so
you guys may want to go back and watch parts of the show again. But I think to kind of sum up the show is compressed music, heavily compressed music, bad. I got a feeling from Black Eyed Peas, still good after all these years.
Still good after all these years, yeah.
And we'll be doing a few more shows this summer for you guys on Tuesday Night with Ben Stowe. I think that's a good way to wrap it up.
Homework assignment. Audacity's free. Grab some of your favorite tracks and analyze a segment and see what the crust factor is. It'd be kind of interesting to see. I'd be interested in just sort of maybe seeing those on the Tuesday Night with Ben Stowe Facebook page, or if you've got another place you want people to, probably be just kind of fun to see.
Even in the comments below here, especially one song that jumped out at me was Katy Perry's, was it Dark Horse, I believe it is.
Okay.
That one always just absolutely drives the subs, because it's just that consistent, and it's like, yeah, that'd be interesting to run that on that particular one. So,
well, and of course, you just made a good point there with the subs. We're talking about, when we look at the whole thing as a chunk, we're looking at the crest factor of the whole song. But if we started isolating parts of it by frequency, we could look at crest factors and you could say, boy, the overall crest factor is this, but the subs are working hard.
Mm-hmm. Oh, and they do on that song.
Homework assignment, viewers. There you go.
There we are. So, all right, Ben, thank you very much for your time tonight. We'll get you going because you've got another show you're going to be doing for a group out on the West Coast. So
Phoenix. Yep, I do. Yeah, it's a 2-video night, a 10-hour drive and a 2-video night.
Nice. And you'll see the family tomorrow. So thank you guys for being with us. Brian and I will be back in about 10 minutes talking wedding music. We'll catch you then.